Okay, thank you very much. Actually, I'd like to thank the organizers of this meeting as well, actually. It's been a great meeting. It's been a huge amount of work for them, I know as well. So I think we should also thank the organizers of the conference. I've certainly enjoyed being here, but I'm also really looking forward to being part of this program. I'm here through the end of the program now, and I'm looking forward to interacting with people a lot more sort of one-on-one for the next few weeks. In the meantime, I wanted to tell you some work in progress on some new work we're doing on radiation-dominated accretion flows. It's very much preliminary. It's very much a work in progress, and much of the analysis is yet to be done, but hopefully some of the results will be of interest to some people. And I really also want to highlight the work that Patrick Mullen, Chris White, Zhang Zhang are doing. They're really doing all the heavy lifting. I'm sort of going along for the ride, as it were. So to start with, though, I was kind of inspired by Yves' recollection of the conference in 2000 to look up what I was saying back then, nearly 25 years ago. Perhaps a bit embarrassing, same title almost, working on the same thing 25 years later. It's maybe not so good. And you'll notice, the nice handwritten view graphs, all pre-PowerPoint, and the very fancy computer graphics we had back then. Actually not so bad. But I think the most interesting thing in looking back was, where were these calculations done? So we were doing numerical simulations of black hole accretion flows, trying to understand MRI and shearing boxes in global simulations. And they were all done in the supercomputer of the day, which was an SGI Origin 2000 at NCSA with a 500 gigaflops peak performance back then. And of course, where are we today? We're at exascale. We have Frontier, which is 1.5 exaflops. That's 3 million times faster than that SGI Origin 2000. That's amazing. I mean, imagine if your telescopes were 3 million times more sensitive, 25 years later. It just blows you away. That's why computation is becoming such an important tool, I think. Moreover, there's just a huge amount of time available on these machines. And so it really is enabling in what you can do compared to what you could do 25 years ago. It's just a totally different world. There is a caveat. There's a technical issue with these machines that, unfortunately, each vendor has its own programming model they want you to follow. So, for example, NVIDIA has CUDA, and Intel has SYCL, and AMD has HIP. And it's somewhat difficult to transition, not impossible, but they're somewhat different. And so writing one code that can run in all these different architectures requires a bit of extra work. I think this has been changed with modern programming tools like Cocos. I've become a huge fan of Cocos. It's just a C++ library which contains templates and abstractions for data containers and parallel execution strategies, things you need when you have a heterogeneous computing system which has accelerators and processors. So if you just write your code in C++ using Cocos, then when you build a code, it'll build into any architecture you want. It'll build into any of these programming models, and then you can run it on anything. So literally, you can move with only changing the build options when you actually compile the code, which makes it extremely convenient. You can develop on your laptop and run it on a GPU accelerated machine without any trouble at all. And so it's very, very helpful. And so there is a new version of Athena. People have mentioned a couple of times. My pandemic, distraction was to rewrite Athena yet one more time into Cocos. It has a full AMR framework, a GR radiation transfer algorithm that was implemented by Chris White and Patrick Mullen. Patrick Mullen doing most of the work for Athena K. One thing I'm excited about is there's now a numerical relativity solver using the Z4C formalism that Dave Rodice and his collaborators have added. We're now doing some black hole merger calculations, computing gravitational waves on exascale machines. It's a lot of fun. It's all publicly available on GitLab, and again, to show that the code just works across whatever, there's sort of a table of performance, and it does excellent weak scaling on various processors, both AMD and NVIDIA GPUs. The numbers are important. I think really what's interesting is that, in my view, the benefit of GPUs is not the speed up you get from a single GPU. After all, they're very, very expensive devices, which are really sort of supercomputers on their own. What really is advantageous is, sorry, I shouldn't have used this. Here we go, back again. Is the ability to get access to big machines. It's just that most of the computer time available in national centers right now are on accelerated machines. So you have to be able to use them to be able to use those facilities. And so that to me is the biggest advantage of the GPU acceleration. So what do you do with exascale? Well, you run 2D MRI simulations. You laugh. What is this? This is actually a 2D MRI simulation. I'm so embarrassed. Yeah. But it's sorry. Well, the thing is, it was run on this was not an exascale calculation. This was actually run on only just 2 GPUs at the institute, but it's 8192 or 8196 squared. This is the current density, out of plane current density. So J, curl of B. And you can see enormous detail in here. In particular, you can zoom in and see that you are seeing plasmoid formation, right? You can see current sheets which are plasmoid unstable, and you're seeing the formation of plasmoids, and these plasmoids stick around for a long time in 2D. They're all over the place. So the point is that we're going to do this in 3D, of course, at 8196 cubed, and that is an exascale calculation. And this was the preliminary calculation to see whether or not we could reach a Lundquist number that was high enough to reach this plasmoid dominant regime, and see whether or not plasmoids really dominate in the fully turbulent regime or not. So that's one thing you can do. It's basically ultra high resolution. I think we're going to hear from James shortly on ultra high resolution calculations, which are becoming much more capable, easy to do with large machines. But the other thing you can do is more physics, more expensive physics. And one expensive physics is radiation transport. So again, it was set up by previous speakers that the radiation dominated regime, dang it, is really very important for luminous accretion disks. And we've got to model that directly with radiation transport. When the radiation pressure is 10 or 100 times the thermal pressure, then the radiation is everything, and you've got to model that directly. So, a group of us have developed a new radiation transport algorithm based on direct solution of the Boltzmann equation, essentially the rate transfer equation in full GR. It's based on this conservative discretization, flux conservative, and we essentially have a little geodesic mesh which tiles the sphere in each spatial grid point, and we store the specific intensity across all 4 pi steradians in each grid cell, and we integrate the specific intensity at every angle, at every grid cell in the spatial domain, and in forward in time, and that way we take moments of that to compute the net heating and cooling rate and the radiation forces on the plasma. So it's a direct ab initio solution of the rate of transfer equation along with full GR MHD, typically using about 100 angles. Right now only single frequency bin, but moving to multi-frequency soon. So this is of course quite expensive because of the extra dimensionality of the radiation field, and this is an excellent fit to these larger machines. Before I start showing you some of the results of this, I also wanted to put it in context that we're not the only group doing this, and there's been some really nice work by Matthew Liska, Hammer Code, along with Sasha and others collaborating on this. They've been doing also radiation-dominated GR-MHD black hole accretion flows for stellar mass black holes with 2-temperature physics as well, ions and electrons with separate temperatures, and looking at the different dynamics of toroidal magnetic fields. There's been earlier work by McKinney, Sadowski, and others. So there's several groups working on this, which I think is great because we're going to be able to really, cross-compare and really understand what's going on in some of these results. So it's a very active field right now, again, enabled by this exascale era. So let me tell you about some of these results, starting with old work, just to set the stage, namely, what's the properties of MRI turbulence in some of these radiation-dominated disks? And this was studied using local shearing box models, so sort of standard unstratified boxes with large radial domains, net vertical fields, with enough resolution to well resolve the MRI turbulence. And so I just wanted to mention a couple of the important results that come from this studies of turbulence, and Omer kind of hinted at this morning. We'll mention some of these results earlier. Namely, one thing that happens is much larger density fluctuations in a radiation-dominated MRI unstable plasma than there is in a gas pressure-dominated case, for very, very simple reasons. The radiation can diffuse out of the compressive regions, and that loses the pressure support, so then the gas pressure is unable to prevent the the compression further, and so you get just very, very high density fluctuation. So for example, when you, I'm not going to stop doing this. When you compare the density fluctuations in a hydro model compared to the, averaged over the box compared to that in rad hydro, there's orders of magnitude difference between those things. And the other thing is that there's radiation viscosity, which comes out naturally of the Boltzmann transport model. When you're solving the full direct transport equation, you have off-diagonal terms in the radiation pressure tensor, and those are the viscous stresses. And those viscous stresses damp the velocity fluctuations. So here's a case of hydro, and here's the radiation case here. My thumb is too thick, and I just keep hitting that extra button. You can see that they look similar, but the scales are different, right? There's orders of, you can't read the scales, of course, because it's so, but trust me, the velocities are much, much smaller in the radiation-dominated cases. So effectively, there's a very large Prandtl number. There's a very large radiation viscosity, which increases the Maxwell stress in that case dramatically. So we've been talking about turbulence and cascades, and Peng and I were just talking about it at coffee, but I think it is yet to be done to study the cascade and the damping of the turbulence in small scales by the physical radiation viscosity. It's a great project to do Shearing-Both calculations with a very careful study of energy cascades and to see how the radiation viscosity produces physical damping on small scales. Yet to be done. Instead, I'm going to sort of transition straight to the global models, because we all want to make global models to compare to the data. And again, Gani mentioned we're doing Cartesian coordinates. So one of our first jobs is to make sure that when you do GRMHD in Cartesian, you can faithfully represent the accretion flow without any anomalous transport from the mesh or any imprint of a Cartesian grid. So we'll be doing the standard EHT test problems for the so-called sane and MAD models. This is the MAD simulation generating, a nice powerful jet along the funnel region, exceptionally low densities. This only goes down to 10 to the minus 3, but our floors are at 10 to the minus 8 in here. So there's extremely low plasma in the funnel region. And then you see this characteristic bubbling of flux ejection that's been seen since Sasha first ran these kind of MAD simulations a while ago. And this is being captured, if I didn't tell you this was a Cartesian grid, I don't think you would know this was a Cartesian grid. It's been captured very, very faithfully. And you can do a little more quantitative comparison and measure the actual mass accretion rates and flux on the horizon. The theta K is the dark blue, and it agrees with all the other codes, most of which are using spherical polar meshes. So it seems that we're capturing, the dynamics for these accretion flows faithfully in this Cartesian mesh. It gives us confidence to move forward with the rad hydro on the Cartesian mesh. So with support of the InSight, we've been running a much longer and much larger suite of simulations, and we're varying the black hole mass. Unfortunately, with radiation, the non-dimensionality of the program or the problem is broken because the capacities depend on temperature, and they're very different for the supermassive black hole versus the stellar mass black hole case. So you have to do both separately. Of course, we're varying the accretion rate, spin, tilt, and so on in the magnetic field. And again, these are preliminary results, but I'll sort of show you some movies and images and tell you where we're going with some of this results. So we're starting with just the usual fishbone Moncrief torus with radiation now, using sort of the EHT initial conditions. This is the same version of it. And again, you can see right away that the density fluctuations in the radiation dominant case are much larger. This is a frothy turbulence with large amplitude density fluctuations. You see that the disk is sort of collapsing a little bit to the midplane. The density at the midplane is higher than it is elsewhere. That's, again, an effect of the rate of cooling. And the enhanced diffusion, it's not just a uniform rate of diffusion. There's convective transport of radiation energy, and moreover, the optical depth is changing dramatically within it because it's so frothy. So it's showing interesting changes when you're in this radiation-dominated regime. When you look at the time evolution of m dot, when the dark blue or the darker lines are the radiation case, the lighter lines are the non-radiation case, there's not much different in m dot, but there is a difference on the flux in the horizon. This is the same model, it's not going mad, but nonetheless, even for this model, there's a factor of 2 difference, at least at early time. So that's kind of interesting. Maybe this frothy turbulence has a different radial transport of the magnetic flux. That's going to be something to look into. And again, to demonstrate this frothy nature, you can plot the optical depth per gravitational radius. And again, you see these holes where the optical depth is 1 or smaller. So again, it's not this uniform diffusion, rate of diffusion through a very, very optically thick medium. You have these bubbles of very low optical depth embedded in the disk. The ratio of flux to energy density tells you where the radiation is free streaming. When it's 1, when it's 0, it's in the optically thick limit. And again, you see this funnel region, which is sort of completely optically thin, strong radiation streaming. There's radiation drag in the funnel region from aberration effects. So we notice there's a difference in the Lorentz factor and the jets produced when you have these very high luminosities compared to the non-luminosities. Again, from radiation drag, that's kind of interesting. That might be affecting the outflows. Again, we're looking into this. So turns out the Fishbone-Moncrief are not a very good model for radiation-dominated disks because they're so hot. They're so thick, they can enormous amount of internal energy. So we switched to using these Chakrabarty tori that Ghani introduced because they have much lower specific entropy per particle initially, and then the radiation field's not dominated by the initial torus, it's dominated by the energy released by accretion, which is what we want, the regime we want to reach. So now all of our models right now are running these thin tori. This is on large scales, and this is on small scales. You see qualitatively the turbulence looks quite thick, that it puffs up by itself just from the release of gravitational binding energy, and inner regions are fairly thick, even though the outer regions are thinner. The movie will go for a while and it's sort of slowed down, and you can see the small scale turbulence. And we have a survey of Eddington ratios. This is at the low resolution initial survey, and the high resolution jobs are all in the queue right now on Frontier. But you can see some interesting results even at low resolution. These are all poloidal slices from Eddington ratios of 100 down to 10 to the minus 2. You see, of course, the disk gets thinner and thinner and thinner. The solid line is the photosphere, and the dashed line is the region where the Bernoulli number is 0. That's the boundary between outflow and bound. So you can see that at very high Eddington ratios, you have this optically thick wind driven by electron scattering pressure and by magnetic fields. And there's still a wind at low Eddington ratios, but it's now optically thin. So you transition from a very optically thick, dense wind from the high Eddington ratios to a very optically thin wind later. You can see right away that this calculation here is not resolved in the midplane. So this is why we're doubling the resolution, and we'll probably have to use more mesh refinement on the lowest Eddington ratio cases to resolve them properly. Chris White is leading a project in which he's looking at tilted disks from 10 degrees to 60 degrees. These have been run at a much higher resolution than that initial study I just showed you before of the Eddington ratio. So there's much more detail in this calculation. This is the 10-degree tilt. The movie takes a while for the accretion to develop. Again, you're starting from a thin torus, starts cooling and getting thinner. The MRI develops, convection develops, I suppose. I mean, it becomes a mess. Eventually, you see an aligned accretion flow in the midplane. It starts generating a nice outflow. And you see in the temperature field, it's a mess everywhere. We don't see this disk breaking. It's only a 10-degree tilt, but it also has not been run long enough. It's only about, I think this is 20,000 M. Sorry, only 10,000 M. So it's not been run, doesn't align to very large radii. These run other models. This is a tilt of 60 degrees. And in this case, this is just a final snapshot. You can see it's broken in the middle. The disk in the middle seems to show different orientations as it spins around. You can see there's little mini disks inside of there, which are at different orientations. So in the interest of time, I just want to mention one more model perfect. You know, Omer told us the importance of the iron opacity bump, which is especially relevant for AGN disks because they're in the temperature regime where that iron opacity bump is large. So Jan Fay is basically redoing the calculations that he's been doing with Omer, but now in full GR and going all the way down to the horizon. So he's starting off with a torus, which extends out to 200 RG, evolving this in full GR. Unfortunately, he doesn't have a really beautiful animation, you know, but instead, once again, you're going to see this much more turbulent. There's a lot going on here. There should be this convection. There should be, you know, we'll see what's going on here. This is a very, very preliminary. These only run this to about 100,000 M. It's not long enough to reach in full equilibrium out to say 100 RG. That's the goal. The goal is to run this to a few 100,000 M and to reach in full equilibrium over a large radius and try to investigate the inner regions of the flow as well as what might be going on at the tens of RG scales. So let me stop with my summary. Basically, it's an exciting time because of exascale. I think it's a huge change. And I think there's much to be done in understanding radiation-dominated turbulence in detail, like this cascade and so on, and as well as doing global models that we can compare directly to data, which is basically what's underway now. I'll stop there.
Very great talk, Jim. I wonder about, you said that the viscosity was very large, so the Prandtl number you said was large.
Yes.
What about the magnetic Prandtl number?
Yeah, the magnetic Prandtl is the ratio of viscosity, but although it's radiation, it's not regular fluid viscosity. So the fluid viscosity is much bigger than the radiation viscosity is much bigger than the fluid viscosity. And so by Prandtl number, I mean ratio of radiation viscosity to resistivity.
Yes, and then you said that the Maxwell stress becomes dominant.
Yes.
I would have actually expected the opposite, but are you sure about this? And what is the motivation? You found this numerically, or?
Yeah, I mean, there's other work that studied the Prandtl number dependence of MRI turbulence, and I think the understanding is when you make the velocity field smoother, the magnetic field can't reconnect on those scales, and so you can continue to wind it up to large amplitudes on small scales, and this just gives you a slightly larger stress.
I don't think it normally agrees with, at least not with my results, but we should, of course, discuss this.
Yeah, okay.
Thanks, Jim. I'm curious, from the survey you've done, do you have any new thoughts or insights into thermal instability in the radiation-dominated regime?
I mean, there's no evidence of thermal instability here that, at least in sort of visual evidence, radial structure of the disk.
Even in the sane models?
The sane models? Yeah. I mean, those models are already so geometrically thick that there's a lot of vertical flux. I'm not sure. I mean, the thermal instability paradigm, I think, would more apply to the thinner disk case. So we haven't done the low Eddington ratio well enough resolved to be able to really say whether there's going to be thermal instability there. I doubt very much it's going to be there personally. If I were to bet, I don't think thermal instability is a big role in these kind of flows for many different reasons, but we don't see any evidence for them right now.
Okay, thanks.
Sorry.
I think you can.
So I was wondering, in the context of and this is probably a question both to you, Jim, and also to Omar, in the context of supermassive black hole accretion, whether you can give any update on the turbulent comptonization.
Chris, excuse me, could you approach the microphone? Sorry, because
I thought I was pretty close already, but whether you can give an update on turbulent comptonization, so the possibility that there's bulk comptonization within the turbulent flow that could potentially, I mean, from an observational standpoint, be relevant for things like soft excess in AGN. Can you assess that from your?
Yeah, so it's a very interesting question, I think. Since these models are gray opacities, you really can't do the turbulent comptonization properly. Yanfei has implemented a multi-frequency transport in Athena++ and run some models to look at comptonization. Of course, we are adding it to the GPU version. We will be running multi-frequency versions this coming year. And one of the things we'll be wanting to look at is turbulent comptonization. But I think it's a very interesting suggestion and a very interesting possibility for producing soft X-ray excess, as you say, and heating in the coronal plasma. But there's been some local turbulent boxes done with Monte Carlo transport to show that it happens, building on the work that Ari, Socrates, Omer did, and others. So I think it's a really interesting idea. But unfortunately, in these models, we can't capture it, but it's absolutely something we're motivated to try in the future. Maybe Omer can add some more to that, please. Yes.
Can I just respond to that?
Yeah.
Sorry. I mean, you can't capture it spectrally. Sorry, you can't capture it spectrally, but you do have it. You have bulk comptonization because of the way you're solving the transfer equation. It's just not manifesting in terms of a change in the spectrum.
Yes, but I mean, the way we have it, but
You can't assess whether it's
No,
going to
exactly.
explain the soft excess of AGN or anything like that.
Yeah.
Right.
Yeah.
Jim, great talk. I'm not going to ask you anything about reconnection because we are doing this already together, right? But
besides, that was only 2D, so it doesn't count.
no. 3D. I mean, we are doing 3D with you. But do you have any comments about polarization analysis from these simulations?
You mean compared to for the X-ray polarization, or?
X-ray could be a style.
Yeah, I mean, I'm not sure you necessarily need the radiation hydro to address these issues, but there's some really interesting questions about the X-ray polarization observed by XP, is it? And she needed to show, along the axis of the outflows, there's, quite far from the source, there's significant polarization. I think these kind of GRMHD calculations done on large enough scale should be able to, should be compared directly to these observations, because I think it's very important to be able to reproduce that. It's a very interesting result, somewhat unexpected as to where the polarization is occurring. And then if our models are not reproducing that, then that's telling us something very interesting.
I just wonder whether you have measured the spectrum of the flows when you have effective high Prandtl number. So
the radiation hydro calculations I showed you before, we measured power spectra, but their resolution was relatively low, and it's, doesn't really show much different from the standard Kolmogorov. That's why I think that redoing those shearing box calculations with radiation hydrodynamics and modern resolution, and then looking very carefully at the power spectrum and transfer functions and so on, can be very, very interesting, because in radiation hydrodynamics, you have a different set of wave modes available to the cascade, and whether that's obeying the same scaling relations or not, we don't know. It's a very interesting question. I don't know if anybody has theoretically worked out what the...
We worked on the normal high Prandtl number, and we found K-1 spectrum, which, but whether this is also applicable to this effective Prandtl number, I don't know.
That's what my concern as well, is that it's not just a inhomogeneous fluid with an actual viscosity. It is a radiation viscosity in an extremely compressible plasma, and the compressibility, for example, might be a more dominant, contribution to the cascade than the radiation viscosity. I don't know. That's why it would be interesting to look at it. Yeah.
Jim, you mentioned a couple of times strong compressibility. So how strong is strong?
Well, I mean, the density fluctuations I was sort of showing you are order unity. It's not that it's like supersonic. It's not that it's shocks generating highly compressible flows. It's just that the effective equation of state, if you like, doesn't allow the plasma to prevent compression. So you just generate large density fluctuations, which are 10 to 1, 100 to 1 compared to the background plasma in which they're in. So large in that sense.
Okay. Mach numbers?
Again, the turbulent Mach numbers are half-ish, something like that.
Okay.
So again, it's not supersonic turbulence that's driving very large velocity density fluctuations. It's rather the diffusion of the radiation field, which removes pressure support from compressed regions and just makes them compressed even more.
Okay, great. Thank you.
So it's not an ideal equation of state anymore.
Before you unplug, can I ask you, in your intro slide,
yes,
you have some waves in the outflow?
And then at the start?
Yeah. What are those waves?
I've wondered this myself.
These.
The first thing you worry about is, that's the grid effect.
They
but
don't
actually,
look,
there's also thermal instabilities and other radiation effects going on here. You see the hammer results. They have these little clouds and blobs everywhere. There's very, very clumpy media. I think that it quite possibly just could be some sort of, mode in the radiation-dominated funnel region that's behaving differently. This boundary between the funnel and is And the disk is very different with radiation as well. And so it's also interesting to look at the dynamics of the interface region, which is where all those things are happening. So sure, it's a very long answer to say I don't know.
Thank you. It's very beautiful. Thank you. Thank you.